Okay.
Hello, good afternoon, everybody. Thank you for coming. It's a pleasure for me again to have here with us Professor Bjarne Stroustrup. I was thinking how I should define my colleague and friend, Professor Stroustrup, and I think the easiest way is to say that he is a living legend of computing. He got his PhD from Cambridge University. Not everybody knows that his PhD advisor was the first person in the world in having a PhD in computer science. So he's a second generation. As many of you know, there are seats over here. As many of you know, he was for a long time in Bell Labs at AT&T, where he developed C++. Over lunch, we were discussing what was the exact year where the first stable version of C++ was available. We agreed 1983, 1984, roughly. I started programming C++ in 1989, so a long time ago. He was there for a long time, then he retired. And soon after, he became a professor at University of Texas A&M. He was there like 10 years, and then he retired a second time. Well, that starts to be a pattern. He joined Morgan Stanley in New York City. He was a few years there again, and then he retired a third time. You see the pattern. And now he's a full professor at Columbia University. You know what? If he tells me again he's retiring, I will not believe him. And today, he's going to talk us about something I think is probably today one of the essences of the C++ programming language. So I still find people here and there when I tell them about C++, they tell me, yeah, that's an object-oriented language. And my answer is, where have you been the last 25 years, if you say that thing? I think, above many other things, C++ is a generic programming language. And generic programming has been evolving a lot in the last years, improving, and I think now Bjarne can give us a new look on generic programming. So thank you very much for coming, and thank you, Bjarne, for being with us again.
Series of emails here the last 2 or 3 days for somebody who was angry with me because he claimed he had proven that generic programming was 3 times faster than object-oriented programming, and I wouldn't agree because it's not guaranteed for all uses and for all architectures and for all compilers. But it's no longer that people don't believe that generic programming works or is useful. It's that I still believe that there's places where it is not appropriate, and I will not agree that it's always 3 times faster than conventional object-oriented programming. Anyway, that was just something I hadn't planned till I got some email here complaining again. I'm talking about generic programming. It's rooted in real needs, and it has a theory behind it. You see the books there by Alex Stefanov, who's the sort of the father of the modern kind of generic programming in C++. And so I'll give you a general perspective, then I'm going to talk about where C++, where generic programming is useful and how, and then the standard technical stuff. And then I'm going to talk about modules and how that adds up and fits with generic programming, because you really need both modules and generic programming. And then just so that you don't think that I think everything's perfect and ready, I'm going to show you how we could do much better. Okay, so the value of a programming language is in the quality of its applications. I am not focused on writing the neatest paper with the shortest examples for a two-column academic format. I'm interested in creating something that developers that build things for other people to use can use and do a good job. And so there's a bunch of C++ applications here, which I think is the real point of the exercise. And we know that none of this is perfect, and that's why I'm still working on it to make it better. And C++ was meant to evolve. There are people who claim that C++ should have stopped evolving back in the 80s. There's people who claim that C was good enough, and there's people who claim that it's not evolving fast enough, or that we should go to something totally different. I knew at the time that I couldn't build a perfect language. As a matter of fact, I have my doubts about the concept of a perfect programming language. Perfect for what and for whom and things like that. So it was deliberate that it would change. We change, the world change, our problems change, and there's a little example there of how something as simple as a for loop over a sequence of elements has evolved over the years. So there is sort of the standard way of going through a vector or an array or a list or something. Today it is shorter and more efficient than what we could write back in the old days using a C-style loop. And if you use range checking, it is much faster. There then also is the expert level kind of stuff. You have a lot of novices, you have a lot of people who just want general performance, like me most of the time. And then you have when you really want to squeeze the last juice out of the machine, and you have the expert level kind of stuff. There it says that it's for parallel on sequence stuff, so you can use threads, you can use vectorization. There's a lambda here who says what should be done, and you better know what you're doing. But if you have a million elements that you want to traverse, this thing wins. So we have to serve all of the users, including the experts, including the novices. And all good engineering relies on feedback. There's people who think that language design is like math. You prove that you have something that's right, and that's it. But what is right depends on what you're doing, what are the constraints on what you're doing, how long time do you have to use it to do it, what kind of people do you have to do it with. So we have to try something, see what works and what doesn't, and then build on that. And basically that's another reason we couldn't sort of start with perfection. Don't know what perfection is, we have to learn. So we evolve to handle the requirements and the uses that change, and try to be guided by real world use as opposed to fashion. Not a great fan of fashion. And evolve it did. There's a graph there, back to one user there. There's Jose Daniel. And we are still growing very fast, and somewhere in the region of 6 to 7 million developers, which is interesting because that means that every one of us who think we know what C++ is being used for are wrong. Nobody knows all of the uses. It's all over the world and other places like Mars, but they don't write code up there. They just use it. But the point is, this is a big issue, and design is very hard because you don't actually know the uses and you don't actually know the users, and what you make in terms of the standards or in terms of a system will last for decades if you get it right, and your mistakes will last for a decade also too. So let's get to generic programming. Here is how it all starts. People want a data structure, a vector of integers, for instance, and they want to operations on the vector of integers. Maybe they want range checking, maybe they want some special operations. Then they want one of doubles, and they realize that the code is very similar, and so they want a vector of objects if you're into object-oriented programming, and then you realize you need to parameterize. You have a concept, you have an idea of a vector, you have ideas of individual types, and you want them to merge them together so that vector is an independent thing in the code the way it is in our minds. And you can parameterize. Once you've got the containers, you want to do operations on them. And so you parameterize the containers, and you parameterize the algorithms. Once you have parameterized your algorithms, you realize that the operations you use in those algorithms also need to be parameterized. So you have a sort function here. Sometimes you want to sort it with the criteria you give it. So we get to here. And finally, you find that you would like a vector of something that doesn't behave right. Traditionally, that's C types. They don't behave properly. Like you have a characters, pointer to characters, which you really know is a C-style string, which is that it is a zero-terminated array of characters. But you know they don't compare normally. If you compare two of those, you compare the addresses, not the values. So you have to do something called specialization that says, this type, I would still like to use it, but when I use it, use a special set of rules. That's specialization. So we don't need all of this all of the time, and sometimes people get confused and think that because they don't need one of these facilities today, nobody needs it, and they're wrong. This is a big world with many different needs. So the templates and generic programming became the backbone of the C++ standard library. Containers, algorithm, concurrency support, timing, random numbers, the works. You look at the definition. They are written in terms of templates using the facilities I just presented. So that's important, especially I was told it was useless, so I like things like this. Anyway, by the numbers, we look at the standard library. There's about 130 algorithms, about 14 containers. And in conventional languages without generic programming, you then have to convert between the types or have algorithms for the different types that you're using and such. And you have an n times n problem, because if all of those containers should be used by all of those algorithms, you get a number of things you have to do like that. If you can break this down by parameterization, you get n plus m, which is 144, which is roughly a 10 times improvement. That's not that unusual, except that's a gross underestimate. Algorithms take many arguments, and if you can parameterize those independently, the The large number up there is too small. Similarly, yeah. Anyway, this is a big deal if you're writing standard libraries for use of a lot of users. It has to be flexible, and yet you don't want to write too much code. So basically, by using generic programming, we approach the flexibility of dynamically typed languages, except that you don't get the cost. We compile away the cost, and you don't get the runtime errors, which is very nice. And if nothing else, it saves you from writing error handlers because the compilers find the bugs for you. So this is sort of the abstract number argument for generic programming. It's not just for the STL. So here is an early application of generic programming. That was at the time the world's largest marine diesel engine. Large as in, see the engineer up there, cylinder head number 5? It's a big engine. All the arithmetic in that thing is controlled through generic programming. It's nothing to do with the STL, it's simply arithmetic, but they wanted guarantees against overflow, guaranteed error handling, mapping to different processes, the works. And if that hadn't worked, well, we would have had it on the front of the newspapers, because you would have had a very large ship adrift somewhere in the Pacific, maybe. It didn't happen. You can write very reliable, very high reliability, very high performance code using this kind of stuff. So basically, anywhere you need to be general, flexible, and efficient, networking, messaging, arithmetic. It is static polymorphism. It's resolved at compile time. So if you have a fixed set of alternatives, you can do this. If you don't have a fixed set of alternatives, if you have to load new types at runtime and such, you go over to the traditional object-oriented world, which is fine. We use the right tools for the right thing. Today, I'm talking about that. The ideal is quite simple. If I call a function f of x and y, I want that to work for every combination of x and y that makes sense. I don't know what f is, but it should take whatever, if it should take what makes sense, and only those. I don't want to wait till runtime to be told that you did something stupid. Okay, any failure has to be properly diagnosed at the point where it happens. Those of you who have written traditional templates over the years know that that was not the case for a long time. I'll get back to that. And the set of type, if the set of types are open, then you're going to do something else. And the constraints, f, x, and y, the types has to be known as a compile time, and performance has to be equal or better than non-generic code, because I am convinced that if you give people something really elegant and it's slower than alternatives, people will use the faster alternatives. This is not true in all domains. Python is a great example of that. However, it is the constraint in areas like embedded systems, high performance, numerics, and things that has to work in small machines and things like that, which is C++'s traditional domain. So what have we got here? If you look at sort of the syntax thing, we want to say I want a function sort that takes anything that can be sorted. Fine. R can be any sequence that provides random access. R's elements has to be compared using less than. It says so in the standard. So why can't I just do what I have on the slide there? That is the right interface to the definition of sorting in the C++ standard. We'll get back to that. And then we can do other things like find if there is a range there, any sequence that can be read sequentially, P is a predicate on the elements of the container of the range that that we're looking for things in, and we have sent back a pointer to wherever we found something. Okay, that's basically the way the STL is made in the standard library. It's just that notation is not up to what we would like. So the standard says that our job, my job as a designer, is to make sure that we can do something approaching that. C++20 allows you to say roughly that, and at the very end of the talk I'll show how it could do it better. And my aim for C++ is to make generic code as simple as non-generic code and make generic programming just programming. It's just the way we would write any other code. That's the ideal. We're not there yet. No, we're not. There's a list of things there on the screen where we would like to improve things for C++. I think for people who know C++, it's obvious we can do better. We should use less C-style code. We should have a better package management and build systems. Functional programming style pattern matching, I would really like that. The point is that most of this interacts and depends on generic programming. So generic programming is all over the place when you write code. And we should think about it a bit more serious than most of us do most of the time. So basically, Alex Stefanov defines generic programming the most general, most efficient, and more flexible representation of concepts. Concepts being ideas. That's fine. We all want generality, efficiency, and flexibility. I used to say it in different ways, but that's the way Alex says it. I want to represent concepts separately. I want vector and the element type of the vector to specify it separately so that I can combine them and get these numerical advantages I showed on the previous slide. We want to combine these things wherever it makes sense, and only then. And I would like to encourage people to abstract only when it makes sense. There are people that abstract just because it's fun. I visited France a few years ago, and it seems that I was told not to use the word abstraction because everybody knew it meant inefficiency, a bloat. That's not what I'm talking about. I want the code to be as efficient when it's generic, or more efficient than if you wrote a single version by hand. I'll get to that. Generality, optimal performance, and the widest range of applications we can get to. So I wrote a paper back in 1981 which explained that we needed generic programming. In particular, we needed to parameterize a vector and operations on a vector. And I conjectured that we could do that with macros. And it took me a year or two to figure out that was wrong. I had the right problem, had a very wrong solution. Macro use is error prone, doesn't scale beyond sort of you and your friend working together. At larger numbers, larger problems, it just doesn't scale. So I started working on solving this problem back in '87 or thereabouts. I wanted generality, which I expressed it must be able to do much more than I can imagine. Zero overhead, otherwise they will use C arrays. Well, a lot of people did anyway, and I could say then you get what you deserved, but that's rude, and we should do better. And I wanted good interfaces. I was the one that designed the functional type checking and such for C, and so I know what I'm talking about. But anyway, I couldn't do all three. Nobody could do all three at the time. You would lose either generality, zero overhead, or the well-defined interfaces. I really wanted better support for generic programming. I couldn't get perfect support for generic programming, and I thought I have to do the first two, otherwise there's nothing left. And so we went for those. We suffered with that for 20 some years. We can now do better. We can precisely specify interfaces, which was the third part of the general idea. Okay, and that follows the general design principles: generality, efficiency, zero overhead, good interfaces. Bing, it fits right in there, and for good reasons. So generic programming, how do you actually do it? Some of you may have written significant code, so let's just go back to the beginnings, especially for people who hasn't seen this a million times. We start with a concrete algorithm, something concrete. Then we generalize until we have made the minimal set of assumptions so that we can generate a really good simple code without losing performance. You can go back and see what Alex Stefanov said, which is this by different words. And we do something called a lifting out an algorithm from something concrete to something more abstract. Okay, so here is the simplest algorithm I could fit on a slide twice. Basically, you can see what we are doing. We are taking the sum of a sequence of elements. Here the sequence of elements are sort of C-style nodes. You have a linked list and you go through the nodes. Here it's an array, and it goes through that array along the way. In each case they grab an element, add it to an accumulator, and then return the result. So for humans it's very simple. We can see that they're roughly the same thing, and so we can start thinking, what would the general algorithm look like? What is it we are really saying here? We have two concrete examples of something. What is the something? Okay, if you look at it here, what we do is we have a sum. It takes some data and returns a value. We start with 0. We go till we hit the end, add the value of the current element, and then we get the next element. Go around and around, and then we return the result. So basically we need a data structure that can support 3 operations: not at end, get value, get next data element, and the value type. We're beginning to separate the algorithms from the type. The type has to be initializable to 0, we have to be able to add, and we have to be able to return a result. These are sort of very general things, so let's look. In the standard library it looks roughly like this, a first cut of it, sum. We take a beginning and an end. We start with 0 of some value type. We go till we hit the end, we add the elements as we go along. Fine. I have introduced some notation here which is very familiar from C. Access a value referred to, get to the next element, check it if we are at the end. And there's some questions here. How do we know the value type has initialization with 0? I mean, there are things you can do here that the types, not all types have zeros. People built matrix types, for instance, where a plain 0 isn't a 0 matrix and such. And why plus? I mean, we've been talking about this adding. Why are we adding? Is there other things we could do to the elements of a sequence? Okay, so one of the fundamental notions in the C++ standard library, which is part of the roots of the style of generic programming we are doing, is a sequence. It has a beginning and the end, and we can sort of go from the one to the other, and sometimes we can go back again. These things are called iterators. I used to call it a sequence. Some people call it a range. And basically a vector of int iterator iterates over integers, a vector of list iterator iterates over a list, so this could be lists, whatever this thing is. It could be for a list, it could be for a vector. And one of the interesting properties is that first could be the same as last, so there's no special cases for an empty container, an empty range. One of the things is that if you have special cases, you can forget them, you can make bugs, and you can get inefficiencies by having to test for them. So this is beautiful. It's general, and there's no overhead. So let's carry on with the example. Here it is again, but what I've decided was I didn't know about 0. I didn't know how, if I could initialize with 0, so I let the user pass in a value. So now we have to say something like this. Here's a bunch of floats. There's 10 of them. We have a double which we want to accumulate into. We pass the double here, and we go through the sequence of elements. Done. This is more general and getting closer to the standard. And we can have the operation be passed in also. Another argument here. We have the sequence that's coming in. We have the initial value. We have the operation. And the operation combines the value of the accumulator with the next value. And now we can take that same float again. We start with 1, which is a good idea. Starting with 0 when you're multiplying, you know the answer. Okay, so we can write things like that. Okay, this is fairly general. It's also almost as general as the standard library accumulate, which it was a pattern of. So it's a semi-real example. But the point here is I started from a concrete problem. I worked my way through an analysis of it and got something in the end that actually compiles and runs very fast. This is simple enough that I can understand it, and the optimizers can understand it, and we get really good code on the output. No indirections that are unnecessary and things like that. Okay, so this is exactly what we are doing for vectors, arrays, lists, input streams, you name it. It has things that works like this. And one of the things that is important, actually, we understand what we are doing more than we did when we started. That is, the code's requirements on its data has become explicit. So we understand the code better, we make fewer mistakes. And finally, we can actually start thinking about when it is explicit, we can actually tell it to the compiler, so that the compiler can use it also. And so here's the general model. Algorithms, containers, they communicate via these things called iterators, which basically tells where the elements are, so that the algorithms can use them without knowing exactly how they were stored. The standard library works with every container having the notion of a beginning of an end. So here's a vector. It has a beginning of the end that's implemented using the vector layout. And we can write algorithms for it. Here's a find from the beginning to the end. Look at the element. See if you found it. Return it if you found it. If you didn't find it, you return the end of the sequence, so that basically what we do is we call the algorithms with a sequence and a value we want to find. If the result is the end, we didn't find it, otherwise it points to the elements we found. That's fine. And we can do the same again. Oh dear. We could do the same again with a list or a different kind of container, or there's even an adapter for doing it for C arrays. And we can generalize by making, let's see, that was a value. oh, here I'm using a range for, which is simpler, so I don't have to play around with iterators directly. Iterators is what a range for actually uses. But the code looks the same, it's just the implementation has become a bit more general. You take the range, not just the beginning of the end, but anything we know how big it is, and it works. Okay, so algorithms are generic. We have container types, we have element types, operations applied in the implementation. And so this is quite general, works for a huge range of algorithms and a huge range of containers. And anyway, so this is roughly where we stood with C++ 98. That's 25 years ago. But we can do better today, but this was where we stood. And the STL and the generic programming techniques that it was based on, and the language features it was based on, was a massive success. They were very useful. They beat just about anything else in the domain for which they were designed, and it was used in many different ways. And that was done despite the fact that there was major flaws in it. I knew when I let this out that it wasn't anywhere near perfect, but it helped enough people. So basically it's verbose syntax, it's duck typing. You look at the code and you look at the template argument and you see if it works. And if it doesn't, you give an error message, and if it does, everything's fine and nicely optimized. Nicely optimized means that templates actually merge information from several contexts, from the template definition, from the argument definition, from the context of where it happened. It gives a lot of information to the optimizers, so it runs really fast. The error messages were spectacularly bad. When you don't have decent interfaces, you have trouble understanding what you're doing. The compiler has trouble understanding what you're doing, and when it gives an error message, it just basically says this doesn't work. And this quite often is from a sub-algorithm that you've never heard of, for a subtype you've never heard of. This is not good. I knew that. I probably underestimated how bad it was, but I knew that was a problem. It also messes up your code generation. You've heard about header-only libraries and things like that that are written just like others, different from other kinds of organization. And the compilation gets slow. Okay, what's wrong here is that we didn't specify intent properly. The interfaces were not specified. When I write the templates, let's see, where's the template? A traditional template. It says there's a type that. What kind of type? What is it that's required? Okay, let's go. So, some of us went to try and solve this problem. Alex Stefanov wrote the book on a lot of this. I did a lot of the language design together with Gabby Dos Reis, and Andrew Sutton did the first implementation of what we are talking about now. So we want to specify the requirement, and so here is find that takes a sequence and try to find a value. So it says we need a forward iterator. An iterator is something that can go through it like this. That's what we want. So we'll have to define what that is, and we want to say that if you have an iterator, I can compare an element indirectly through it, and that's indirect equality comparable. It's a long word, but it's in the standard library, and you need things that aren't too short because they would clash with everything. Here we have the forward range. That is, instead of having a pair of iterators, we say we want something that has a beginning of the end. And then, since it has a beginning of the end, we'll find what it is, and we can do something like that. And then equality indirect inequality comparable is if you go for an iterator into R, that's what you want. And given something like that, I can now say find 7 in the beginning of the end. Try find of 9. It works. It's a vector. It's a range. It has a beginning and the end. That's fine. We can try this beginning end. 1 and 3 doesn't define a range. It's just a pair of numbers. Error or compile time. It's not a forward iterator. A forward iterator you could define as something that has a beginning of the end. 1 doesn't have a beginning or an end. Okay, find 3. It's not a 3 is not a range. Find in the vector of integers high. Well, vector of integers doesn't compare with strings, so that's an error. And I can try nah, that's not okay. That's another bug. I should have defined a vector of 2. That was what I meant to do. A vector of strings with a different name. I'll have to fix my slides. Thanks. Anyway, for the right kind of vector, that would work. Notice that I used a C-style string here that doesn't compare it properly. I'm asking it to compare addresses. That would never work. Okay, so we've always had concepts. This is one of the things I noticed fairly early on thinking about this. You read K&R, Kernighan and Ritchie, the book about C from 79, and Dennis says, well actually the definition says something. It's actually Brian Kernighan that wrote the words, but says that we have arithmetic types and we have integer types and things like that. And what are they? They are the things that certain algorithms like plus can work on. And there's a definition, there's a list of things that says what is an integer type, there's a list of things that says what is an arithmetic type, and each of those have a set of operations that you can use, and then the algorithms, the basic algorithms, will require those things. So they've always been there. And then the STL concept, iterator sequences, containers. Well, we've had them for a long time, but if you look at the early definitions, a container isn't there. There's only iterators and sequences. The fact that there's no containers means that we have to go through this begin and end business for a vector. It doesn't simply take a vector and realize that it knows how to get from the beginning to the end of the elements. Graph concepts, edges, vertices, graphs, DAGs and such. There's lots of these things. The textbooks are full of them. What we're doing with C++ and with concepts, as we're talking about now, is simply to somehow express it so that a compiler can understand it and use it. And we need direct support, and we have it now. So a concept is a compile time predicate. So the way this works is you can ask some questions of a type. Are you an integer type? Are you an iterator? Or whatever. It's a compile time predicate, yes or no, and we compile it, we evaluate it at compile time, and you can define these things. We define the basic ones in terms of use patterns. You can read a paper by me and Gabby from 2006. It's not a recent idea. And here is the way we define equality comparable. That is something that can be compared with equality. Okay, you take two types here, type T and type U, and they are equality comparable. If equals, it returns a Boolean, not equals, return a Boolean, and you can flip them around. This is not just one way. You can compare it and it works. And I have a default value for U, so if you only give it one type, in other words a homogeneous definition, that's fine. And you don't have to do this yourself. Like for all basic things, we provide standard support, and in concepts, the header file concepts, you find this one actually. Okay, so if you want to test whether a type matches a concept, you just evaluate it. You evaluate it at compile time. Static asserts are run at compile time. So if I want to know if int and double are equality comparable, I just call that function. It's after all a function. Slightly odd notation. It uses angle brackets instead of parentheses, but that's fine. Also, it uses the types, not values of types. So basically, we are computing in the domain of types. Assert is not equality comparable int and string. Yep, they are not. The test here fails. And you can take something that whether my type is regular. I don't know what my type is, so I don't know the answer here, but you can do that with any type to check whether it can be used for places where you need equality. And we don't actually write out elaborate rules for how these concepts relate to each other. We don't build DAGs, we don't build class hierarchies. That gives us a great flexibility. It is just a function. It is just something we say, given a set of arguments, what are the answer, yes or no? This is very, very flexible. Okay, so usually, of course, like when you write code, you don't actually just write it in the language itself, using just plus and minus and for loops. You actually build functions that allows you to say things more regularly. So here's where sortable range is. We're getting back to the original examples. Is it a range, and is it sortable? If I want a forward sortable range, is the range forward? It's a forward range. It has forward iteration, and can you compare the elements? So this is the one I need for sort. This is the one I need for sorting a list if I wanted to. It's also the kind forward sortable. Forward range is something that you can go that way on. A random access range is one you can sort of poke into. So I can now use sortable range. I put the autos in the wrong place. A sortable range will sort vectors. A sortable forward sortable range will sort lists, because the lists don't have the ability to poke at the elements at random. Therefore, if you call it, if it can do all of this one, it will. Otherwise, it'll do that one. How does it know? It simply looks at the properties defined to see whether they're subsets of each other, which they are, because a forward range is a subset. Sorry, the random access ranges are a subset of things you can traverse from one end to the other. Okay, again, we don't have to declare that one relates to the other. The compiler figures that out. Here's an example, a simplified version of the advanced algorithm in the standard library. It takes a forward iterator or a random access iterator. The forward access iterator goes laboriously through the sequence the way you must do with a linked list. The random access iterator knows that it can do random access, so it goes right over there. It doesn't have to do the slow way. And so if I take a vector of string and a list of strings, the vector of strings, that one there has random access, so it uses the fast algorithm. This one here can't use the fast algorithm, so it falls back on jumping along one element after the other. And again, we don't have to say one is better than the other, it's computed. So from my point of view, concept benefits is they actually support good design. It allows people to think about what they want to say and have the compiler check it. Having to think about what is right and what isn't for the combinations is good. It leads to better design. Yes, some people who don't like to do it because it involves thinking, but that'll have to be. We get reliability and maintainability. The compiler knows more. The static analysis tools know more, so they can give you better feedback, and you can start overloading like I did there. I had 2 versions of advanced, and we can pick the right one easily without saying anything. And so there's people who says, I don't need this. This is just overhead. And so one argument that I sometimes use, remember when we had built-in types and no classes? Just that. I remember that. I was around in the 80s, and there's people who still write in C where they only have that. So never in C++, it's like C today. At least now C has function prototypes. It took 10 years to get them to accept that. Okay, concepts and types. Some of you might have said that a concept looks awfully like a type of a type. And a single argument concept is very much like the type of a type. So basically a type specifies a set of operations that can be applied to an object, implicitly or explicitly. It relies on function declarations and language rules, and it specifies how the object is laid down in memory. That's what a type is in C, C++. A single argument concept does exactly the same, slightly different. It relies on use patterns and other concepts. It says nothing about the layout of a concept, which means that if you define a function that takes a concept, you have defined something that is significantly more flexible and general than if you had defined it to take just a type. And that is one of the advantages of generic programming, is that you don't have to be quite as precise about which type you want, because once you've specified the property, it'll take any type that matches those properties, that has those properties. Okay, so my ideal is to use concepts in most places where we now use types, except at the point of definition of the type. Okay, so objects can have only one type. An object class can be used in one hierarchy. Once you parameterize it, an object doesn't have concepts as such. So it fits more concepts. A concept is just a predicate. And concepts are not intrusive. It's not something you have to declare for every type, and so it requires less foresight. Okay, and it increases the amount of type information we have available to the compiler, to the human reader. And so basically types and concepts documents intended use, and from a lot of stuff follows from that, including better information, better compile time, error handling and such. In general, overly general types can cause problems. I mean, if I see code that uses void star, I start wondering, what on earth is that actually pointing to? But you know, it's worse than that. The compiler looks at the void star and says, this can point to anything, which means that anything within there can be an alias, which means that I have to back off any optimizations for any pointer that might point to the same thing as the void star that is flowing there. So if you want to poison the optimizer, if you want to poison your program so that the optimizer doesn't work, Just stick in a void star here and there. It'll slow down your code marvelously. This is of course what a lot of C code does, and C style C++ code. We don't want that. Template type name can be any type. Means we can't really understand what's going on. It means that for checking we have to look at the whole definition. It's a lot of work. The compilers get slow and we get error messages far too late. And you can do that again with lambdas and plain old auto. It can be any type. Hard to read, hard to optimize. Okay, so one of the ways of looking at it is auto is the weakest concept. If you say f of auto, it simply means it'll take anything of any type. Ta-da! How do I implement something that takes only that'll take anything? Not great. I could even define auto with concepts. There's a concept auto, which is true, which basically means that auto means that it must be a type. That's all it means. That's not very much. So basically I accept concept where auto is a type in C++ that says I will deduce the type from the initializer. And it'll then take that type and keep it forever after. It's a static concept. It's not a dynamic facility the way it is in dynamic languages. If you want something like that, use the library type any or variant. But here, and it's backed. The committee accepted auto first of all. This is actually quite interesting because when I first discussed some of this stuff in 2002, I showed them a function auto f of auto, which takes anything and returns anything. And I've never heard screams of horror as loud as in that meeting. Then they went and accepted it 10 years later without the concept that allows us to constrain what's going on here. And yeah, I mentioned that. 2003, I got the year wrong when I spoke. Ah, well. So type deduction. Here, sort of VI. If I have a sort that is defined to take a range, this will work fine. Here, it'll take a range. That's fine. No, this is template argument function types. It sort of sees what the type is, and it then uses the deduced type for the instantiation of the template. But we can do further. Here's auto, as I mentioned before. That x is an integer because 7 is an integer. Floating point auto. Why? It says I will take whatever comes out of foo. It's some kind of type. But I won't just use it to give the type of auto. I will just check whether it's a floating point. So that floating point is a concept. So it will take the value of that, the type of that, make it the type of y, provided it is a floating point number. This is useful in arithmetic. And here you can say I want to iterate over elements of y provided the elements are of an integral type. So you don't have to write very much now. You have the full constraints, but it'll work for all the type that meets the concepts, meets the constraints there. And one of the places where this turns out to be really nice is that you have scoped locks when you're writing concurrent code. That's a very nice facility. It acquires all of the locks or none of them. Actually, it stops until it gets all the locks, and it doesn't create deadlocks by grabbing the mutex 1 and then waiting to see whether it can get 2. Somebody might do it in the opposite order. No, it gets it right. But the point is there's different kind of mutexes. Quite a few kinds of mutexes, actually. This one doesn't care. It simply deduces the type of the scope block from the type of the mutexes. And here's one of my favorites, a span S of A. I want to declare a span. A span is something that points to an element and knows how many elements that it can access of that first element. Okay, fine. There is it's an array. This has to be something that has that has a fixed number of elements. Otherwise, I couldn't deduce the type. But furthermore, I can deduce the type of the elements of A and make it the type of the elements in span. So compared to a lot of writing, this looks short. It's just what I wanted. I don't have to tell the compiler what the compiler already knows. Quite often, the compiler knows it better than I do. And so it shortens the code. If it starts looking like dynamic dynamic language code, fine, but it is not dynamic. It still runs at C++ speeds. It is still checked at compile time as ever. Let's see. Let me move on. So basically, we need to generalize and make precise our interfaces, and that's one of the keys to good programming in any language, really. But we're talking about C++ here. Overly specific interfaces, which we have a lot of in C++, they're defined to work only on ints or only on doubles, and you get a lot of conversions there. And you know you can get into trouble with conversions. If you have a function that takes an unsigned, what happens if you give it -2? What happens when you give it an integer whose value is -2? Nothing good comes out of that. So it's much better to have the interfaces precise, saying I want something with these properties. Imprecise interfaces lead to errors. Overly precise interfaces leads to conversions, which can be trouble. And then resource management. I'm not talking about that today, but really use ownership abstractions like vector, map, and stick to RAII. Resource acquisition is initialization. Then you don't get into memory leaks and memory misuse. Okay, so to notation. In 1980, we got this notation here, double square root of double, and we can call it like that. And if we call it with something that isn't a double, we get an error right there. This is fine. This is C++ vintage late 79. It is also C today. In template function from 88 or thereabout, you have to you put the definition up, the whole definition up in a header file, and declarations are rarely used. That was not the way it was meant to be. It's very different from the way we organize our code with traditional C and C++ with code files and header files. This all goes up in the header files. And if you do something silly, you get an error message, and it's quite often a silly error message, very large. This is not good, and well, some of us knew that, but couldn't do anything about it. Today, we put the definition into a module, which is sort of like the .cpp file, and then you deduce the interface from it. You can simply saying it's exported from the module, and then we calculate what the type is, what comes out, and the use is just like that. And yes, that's silly, equally silly to that, but you get a better error message, because the compiler, just like you, know what is required. Also, there's many notations for this because there's many uses. You can write templates, type name, iterator. That's the C++ 98 version. You can constrain them by saying it requires a random iterator. Sometimes for complicated requirements, you get an explicit requirement clause, and you can simply say, put the requirement in. Instead of just saying it's a type name, you can say it's a random access iterator. Then you can do traditional functional thing that looks like that, and well, There's ranges here. This was done with iterators to take into account that most of what people know today is iterator based. So let's see how we do it. Use higher level concepts. Look how you could specify merge with using just the plain concepts here. There are 3 iterators needed. There's a forward iterator, there's another forward iterator, there's an output iterator, there's some assignment requirement, some more assignment requirement, and then you have to be able to output the thing. This is sort of fairly long-winded. It is exactly what's required in the standard. It's headache inducing, and if you think this is not bad enough, try accumulate. It's far worse. So what we do is exactly what we did when we are having ordinary code. When you have a large chunk of code, you make a function that does it so that you can use it in different places. It happens to be that the merge requirement is common to 4 algorithms. So this is something that we need 4 times. So we define a function mergeable. Give me 3 types that has the mergeable requirement, just like functions. And many of the algorithms take multiple template arguments. So this stuff works, and about half of the standard library needs requirements that takes more than 1 argument. After all, if you have a function with 2 different types, 2 different argument types, there must be some relation between those 2. Why else were they in the same function? In many cases that argument has no answer. You can think of some cases like you have an error message where you pass the error string, but quite often if there's 2 argument types, there should be a relation, so you end up writing something like that. And here's the mergeable thing. I've just taken the code, stuck it into a function, given the parameters, done. And again, you don't have to do it. We've already done it. It's in the standard. Just go and use mergeable. What make a concept good? Represent fundamental concepts. Have a semantics. We found that people started writing this stuff, including us, look too much at the syntax. The syntax has to reflect the semantics, and a good concept is something you can say what the meaning is, what the semantic is. And usually you have a cluster of operations that are required for an algorithm to be useful, and that is what the concept should reflect. Not a whole bunch of individual things. There's people who write addable, subtractable, multipliable. Those don't have any real semantics, so avoid those. It is not quite the minimal requirements for an implementation. So generic programming aims at finding the minimal requirements for an algorithm. But if every algorithm had its own concepts, we would have a trouble remembering things, we would have a trouble documenting things, and the minimal requirement is often for a specific algorithm, not for a general algorithm that can be implemented in a variety of ways. The classical example is if I looked for a minimal requirement for or some example in the case where I wrote accumulator plus element value, then I would eliminate the use of plus equals because that was not used there. So the things get somewhat unstable. What you want to do is to have concepts that represent general concepts. Concepts are called concepts because that's what they are, but it's sometimes made difficult to talk about them. The naming of concepts were done by Alex Stefanov, I think 30 years ago. It's not a new thing. It's been in the C++ community for decades. Anyway, it's not the minimal requirement, it's the minimal requirements for the general concept so that it can support interoperability and be reused and remembered and things like that. One of the problems with designing concepts is that if you don't get it right, you get, for instance, dozens of concepts to define an arithmetic type. And arithmetic, look at the arithmetic, it only has about a dozen fundamental concepts. Look in your math book. And if you end up with 50, there's something wrong with the way you are defining your things. Good concepts support interoperability. There should be relatively few, and we can remember them. Some of you have heard of template metaprogramming. I have been talking about functions all the time because the emphasis in this generic programming is on functions. Even type checking is evaluation of functions. But people also use it to construct new types. This is often called template metaprogramming. Here's an example. We have a type pair that takes two types with one element of each, and then I want to write a constructor from another pair. And I can do that provided the first element is assignable to the member and the second element is assignable to the member. So I can express this. Once you look at pair, which is a bit of a horror, but writing this in any other way than simply stating what it is you want becomes very, very complicated. There's something called SVNA, and there's a standard library called enable-if that allows you to write total messes that expresses this. It's like writing a simply code where this is the high-level code. This is what I wanted to say. This kind of stuff is implementation detail, which for the last 10 years have leaked into application code where it doesn't belong. Okay, template metaprogramming. You can have a factorial of a function. It looks like that. And when you say fac of 40, it's an odd syntax, and you need unusual programming techniques when it's anything more complicated than just a fac. And what happens to the compiler? It generates 39 types to generate because it iterates 40 times, and it leaves those types in there forever, bloating your compiler's memory, slowing down your compilations. This can be horrifying. So basically, I didn't anticipate this, and it doesn't actually work all that well. But I have seen very reasonable, very competent people writing things like this, except that they were this much code, and they did it because nothing else could do it as guaranteed and as fast generated code as, I mean, nothing could beat it. I know, I was there. I was trying to get rid of it. I couldn't. So yes, people only do these things either because they don't know what they're doing or because they absolutely need it. But this is wrong. What we want to do is that this is a function. I know what functions look like. They look like that. So all we need to tell the compiler is that if n is a value known at compile time, please compile it. Please compute it. And that's what it does. Fac of 40 will return the correct value, and that's it. You don't have to learn much here. It just works. Ordinary syntax, ordinary techniques, non-transient use of compiler no non-transient use of compiler memory. This is just much better. This is what people do today. This is what they did in the past. The problem is that a lot of programmers are stuck in the past. This is an example of how generic programming and other programming facilities merge into each other, because quite often this is a parameterized thing, but big examples didn't fit on the slide. So back to this program organization. The idea with C++ is that you have the types, the interface needed in the header files, you have the implementation in the implementation file. That's a good concept. The problem is that with templates, just about everything goes into the header file, but a header file has to be compiled every time it's included, so it gives slow compilations. In the dark old ages, 5% of your code was in header files. Now it's not uncommon to have 95% of the code in header files. This is a problem. So let's solve it. Here is the traditional solution. Include A, include B. Unfortunately, it can be different from include B and include A, because the first header file you include can interfere with the second header file you're including. You don't want to do that, but the compiler doesn't know that, so it has to check. Furthermore, include is transitive. So if I include your file, and your includes his file, and his includes her file, if there's something in her file, I can now use it, whether I want to or not. There's a classic example. There is a max macro somewhere in Linux that I have to protect against so that I can use max. Ta-da. Anyway, subtle bugs. With modularity, we want to import A and B to be the same as import A and import B. We want it to be non-transitive. If I want to export something from my module, I have to say so, which means I stick the word export in front of it. It's not complicated. Much of the compilation can now be done once only, whereas this has to be repeated every time you include it. And it's hard to do this. And if you want more information, you can listen to this CPPCon talk. By the way, if you like watching videos, the CPPCon videos, there's a lot of good ones there. We pioneered the idea that all conference talks go on the web back 6-7 years ago. Okay, so here is the example. It's a small one to fit on the screen. I want to make a module called a map printer. I want to take all kinds of good stuff and use it. And then I write my one function that I'm going to export. It takes a sequence. It prints a map by key value pairs, output here. The point here is that the interface, the type that is exported, the name of the function and its type is calculated from its definition. And all of this stuff doesn't leak out. You don't really want my using namespace declarations to leak out into the world the way it would be if it was in a header file. So this makes code simpler, less things depend on each other. It gives the compiler and optimizer better opportunities, and it actually works. The question that was asked many times was that can you afford it? I mean, I don't really want to keep track on all of those standard header files. They're a barrier to entry. It is a nuisance even for people who know them well. So I did a small experiment. I did hello world with IOStream or import std. And here's the timing. I included only the needed headers here, IOStream. I imported, import the whole standard library, include all the headers there, and import all the headers. And we got these numbers. Thing that's interesting is that when I write that program, it compiles 10 times faster than just including what is needed. So I can grab the whole library, and these days I always grab the whole library when I'm writing things with the standard library, and they all cost about that. We can try and use stuff of this, see if it costs a lot. I took my nine favorite headers, imported and included them, used a little bit from every one of them just to make it fair, and there the advantage was only 5 times faster compiles. It is not uncommon to hear people saying, well, I got 25 times, I got 50 times. My sort of guesstimate for the average is about 7 times. If you have a compiler server farm for compilation and you're using now 100 computers to do that, you can probably get away with 10 in the future. This stuff works and it is shipping. It varies in quality for different compilers, but we're actually trying to do something that improves the compile times by a factor of 10 to a technology that has been successful for 50 years. It is fiendishly hard to make people convert, because they've got billions of lines of code, and this include model and what's right and wrong using it is wired into people's heads. But basically you can take larger chunks because they're very close to free. Okay, so are we there yet? I've been saying a lot of good things. I've shown improvement over the years, and just to make sure, I'll show you what doesn't work too well in my opinion. So here's a list sort. One of the easiest way of sorting a list is to copy it into a vector, sorting the vector and then copying the elements back again. There are algorithms for sorting lists that is supposedly better than that, but for most needs I have for sorting lists, the lists are not too long, and this stuff beats just about anything. Okay, so I write my algorithms with iterators. There are 2 iterators, input and output. So let's see. Why do I have an output? Oh, I have to clean this up. Anyway, I make a vector of the value type of the thing, copy the elements in, do a begin and end, and then copy them back again. This should be the beginning. This should say the beginning again of the input. It's the iterator first up there. Okay, currently we can do this much of it. We can do ranges, so we get the value type of the ranges. We still have to initialize it with the sequence. We can't iterate or just over R to make a copy of the vector here. And sorts, I have to put ranges in front of it, and when I copy back, I can copy from the vector to the beginning iterator, that one I got right, of the of my input. But why can't I use a range there? I want a range so that I can, in general, I want a range so that I can check that there's the right number of elements and get range checking. So it's a major improvement. This is good code. It runs fast. It says roughly what I want. There's actually no problems with overrun there because I correctly used this one, but I could make a mistake. What I really want is something better, but here's what I can do today. I could actually hack the vector so that it could take a range. This is what I want to do, right? I want to initialize the vector with the values of the elements of R. And I can do sort. Why do I have to say ranges sort? I just want to say sort. And I want to copy to an output range. As I said here, it doesn't actually matter if there's enough, but here there can be range checking. And yes, I've got this thing. And yes, I've hacked this one. But it's still not good enough. We can do better. This is what I wanted back in 2004. I wanted to sort a forward range, which is a list and the kind of thing R, by copying into vector, sorting the vector and copying back out again, and I wanted this one to be an output range deduced from the fact that this will be declared to be an output range for copy. I mean, I can now have concept that says that's an input range, that's an output range. And copy just requires forward iteration. Sort, it's a will be a random access range, and this copy is done. This can be done anyway. I don't know why I have to write auto there all the time. That was not something I wanted back when I thought about this, but the standards committee decided that it was very, very dangerous for you not to know that this is a template. They wanted to know the difference between a template and a function. You can't really, but that's what they wanted. So I'm going to propose that. I'm writing a paper on it. So basically, generic programming, if you want to write generic programming, I suggest some rules. Basically, you constrain almost all template argument with concepts. The almost is usually to do with template metaprogramming rather than template programming. You can specify your interfaces. Ask yourself, if you are saying just type name instead of a specific type, you are writing with something equivalent to a void star, or writing in C without specifying the function arguments. You would never do that. So use the concepts. Constrain the variables will improve readability. It'll force you to think a little bit. And algorithms should use general types so that you can get plug and play. It shouldn't be that every function has its own concepts. That goes down to that thing here that use name concepts. Don't use the low-level facilities for expressing constraints. Define a concept, name it, use it. And user level, application level concept should have semantics. Think about what it means, think about what the requirements are for correct semantic use, not just syntax. And you can always check types against concepts if you want to by using a static assert. And here's a bunch of reading material that you can follow. I'll make the slides available after I've fixed the bugs. I've never figured out how to get the compiler to check my slides. I like compilers. They're good for getting code correct. Okay, questions?
Thank you. I assume you have questions.
Hey, first, thanks for the talk. And secondly, well, along the talk, the Alex Stepanov was mentioned a couple of times, and the regular concept showed up. So, given that in Alex Stepanov's books and such, regularity is at the core of it all, and at the core of the first version of the SCL, since you've been through all this process of evolution of the language, how would you say that the importance of regularity has changed, if it has changed at all?
I didn't mention regularity here. It's not because it isn't there. It is in the standard, but going into too great details about which concepts were useful where, I didn't find it to fit here. The most important concept probably are regular and semi-regular. For those of you who's not deeply into this, a regular type is one that sort of behaves a bit like an integer or a vector. That is, when you copy it, you get a copy. You can copy it or move it. If you compare it, you're comparing the values, not pointers or things like that. It's basically a type that behaves in a regular manner. There has been great debates about whether regular should include equality and less than or not. And I don't want to get into those discussions. Alex wants regular to include comparisons because he claims every bit pattern can be compared, if nothing else. And I'm sort of on the other side. Semi-regular doesn't require, let's see, I get confused. This is at the end of a long lecture. But the difference is the comparisons between semi-regular and regular.
Okay, then, thanks.
More questions?
Thank you for your talk and mostly for your work, which is has been very inspiring for many people for many years. So thank you. It's more a curiosity than a question. There's a great resemblance between the concepts in C++ and the family types in Haskell or functional languages. So my curiosity is, how have you been influenced by other languages, or do you look at other languages when considering how to incorporate new construct into C++?
Let me answer the concrete question first. We looked at other types, including Haskell, and most of those languages are focused on the notion of a type, and they are focused on the idea that you define a type roughly the way you define a class. And classes and types of types are not as flexible as general functions. And we tried, reluctantly in my case, but we tried to find a model for concepts that was based on classes and operations on classes. That is, you identify a type and you specify its requirement. It's very hard to do if you have mixed mode arithmetic, that you can have add with different functions. A lot of those languages are homogeneous. It is very hard to deal with the fact that we have conversions, too many conversions, and some of them has to work. And it's also much harder to specify multiple argument concepts in that type of type model that other languages mostly go with. So C++ tries to deal with multiple types, tries to deal with implicit conversion, tries to deal with mixed mode arithmetic, and for that reason our project to define something that looked like others failed. It is interesting that my first paper based on this idea preceded that effort, and it came back and it actually solved the problems it was supposed to solve. So yes, we did this. Gabby has taught Haskell, and it's yes. In general, was the second question, or the general question is, how do we consider? Was it how we get features in, or what features we get in?
Mostly, yeah. What's the process? How and why and when?
Okay, the committee has endless processes. I don't. I look at code. I look at problems. I listen to people. What works, what doesn't, what's not fast enough, what's fast enough, what is it they can express easily, what is it they can't express easily, what is it they can't express at all. Listening is a major part. And then I try to create archetypal examples, archetypal examples. try to boil down so that I can think about it without getting lost in other details. Notice I was using sort, find if, and vector, and list all the time here. These are very simple, fairly concrete examples of how you can discuss the concepts, the general ideas. And I consider them a sort of, well, archetype of other things. A vector is an archetype of a lot of containers. As a matter of fact, the ideal for most of the containers. Sort and find if you can do those, you can do so many other things. So it is actually fairly similar to the notion of how you do generic programming. You find what is requirement for a large class of problems, and then you try and solve it. And you try not to come with over-specialized solutions. You try not to just solve a particular problem. You have to think about things. I mean, facilities has to do more than I can imagine, because a group like this can imagine much more than I can. And this is true for all groups, really. So that's basically the idea. And the first solution is rarely the best one, so you have to work on it. And then you work under the constraints that you mustn't break all the old code. I mean, people have billions of lines of code, and you have to be able to teach what you're inventing. I claim that generic programming with concepts is probably simpler than ordinary C code, where you have to do all of these casts and implicit conversions and stuff. But you still have to fit it into that universe where people live. And then you have to make sure it compiles fast enough and it runs fast enough. But first of all, you find your examples and see how you really like to express them.
So first, thank you for your talk. Let's say you're writing a generic function, so you stick in a concept to so that the compiler checks that the type fit by the user is okay. But is there a way that the compiler can check that the implementation of your generic function is not using something that your concept is not requiring? So let's say you are requiring a forwarded iterator, but then you are using it in the generic function as a random access iterator. Is there any way of making the compiler check it?
Okay, this is the problem that's often referred to as the template definition problem. That is, when I write a template, what if I use operations that was not specified in the interface? And I used to think that you should be able to do that check, do a complete check of a template in isolation. I don't think so anymore. There are two reasons for that. One is that for a general user, 95 or higher percentage of the benefits come from checking the interface. That is, you have given what is required for the core algorithm. Implementers could use a bit more checking, but very few implementers, probably less than 1% of the whole population, and they're smarter, so they can handle the problems. The other problem is that I find that there are other things in an algorithm or in a type definition than are reflected in the interface as seen by the users. So real code don't just do what it's asked to do. It does things like debug information, tracing information, reporting back to base and things like that. I forgot. I'm tiring. The point is that there's a lot of sort of scaffolding that are part of the implementation, and if you've written functional programming, you know that if you change the implementation, the interface, the implicitly generated interface from the implementation changes, and now there's a set of changes cascading through the call chains. In a lot of stuff, one, we don't want that. Two, we can't afford that. And so I would like better checking, but only if I can find a way of expressing exceptions to say that there's some debug information here and it's using I/O streams. I don't want I/O streams in my in my functional code. And maybe tomorrow I won't use I/O streams, I'll use my firm's log system. And things like that happens all the time. The more code you have, the more sort of industrial it is, the more often you have stuff in the implementation that is not reflected in the interface. And one of the extreme cases, there are people in the committee now representing large and important organization that says definition checking happens over my dead body, which means that it won't happen unless we solve the problem of expressing what is it that doesn't need to be in the interface. And I don't really know how to do that. One thing to point out, it has nothing to do with the model. It's nothing to do with the fact that concepts are compile time functions. Gabriel Dos Reis wrote a little language testing out definition checking for this model. We can do it. We've known how to do it for more than 10 years. It's just we decided, no, we're not doing that. It has too many bad side effects. And it's still compiling very fast. So we, at the current rate, we've just improved compile time speeds with a factor of 7 or 50, depending on what it is. Getting another factor of 1 or 2, well, maybe some other year.
I have a couple of questions, if I may. There was a proposal some years ago that didn't go anywhere about the idea of using concepts to automatically generate runtime wrappers around types. So for instance, let's say I have a concept for a shape, so I can have a sort of automatically generated any shape, that type erasures, anything that satisfies the shape concept.
Okay.
So how do you like that idea? It didn't go anywhere.
Okay. Two things. One, I don't like that idea. Two, you're going to get something similar, possibly even in C++ 26. We are working on static reflection, which is the ability to write a piece of code that looks into the compiler's data structures and can ask questions about types and then inject code based on the computation. The original definition of that was one of these object-oriented things with lots of hierarchies and lots of explicit dependencies. We just got, at the last standards meeting, agreement not to go that way. The new thing is based on compile time functions. They're called const express functions and const eval functions. The difference is const express functions can work for runtime values. Const eval must be done for compile time entities. And the current reflection work is based on the same model as concepts, as constant evaluation, constant thing, and we might actually get it. And so I wrote a paper once about 6 key use cases I wanted done, and we'll be able to do them. One of them is to write a I'm tired. Generate very specific input and output operations. take a function and generate an output operation based on its members and things like that kind of stuff. The other one I had was to generate a map. Name, offset maps. So the reason we are doing this statically is that we found that the cost of dynamic reflection, the way you have it in, say, Java, is pretty bad. One example was we took a game, one of the more popular Microsoft games, and the code was 80% and the data structure is 20%. When you ran it through C++/CIL that generates data for reflection, it was now 20% was the code and 80% was the overhead. In other words, if you have that as the default, you lose the whole embedded industry. The other problem was that it turns code in a typed world, strongly typed world, and I keep wanting to C++ to be more strongly typed from the very beginning. If you do that, you move it into a thing where instead of type checking, you basically have a graph algorithm where people run through a data structure and do things. No, he doesn't agree. Anyway, whatever you don't have, I don't think you have that problem with static reflection.
Okay, I think maybe I didn't explain my point exactly, but just let me give it another try and we can forget it again. So let's say you have a concept for, I don't know, something that can go into cout, a streamable thing, okay? So if I have a number of unrelated objects that are all streamable, I can write some sort of wrapper, some sort of any streamable thing that basically takes any type that is effectively streamable because it satisfies the concept, and then provides, just as any is basically a proxy for auto, for anything, or function is a proxy for something that is callable, this any shape or any streamable thing will basically do the scaffolding automatically in order to be able to generate these runtime.
I think we have a language problem, and it's not a programming language problem. I thought I answered the question. Basically, the way you would do it was exactly to write a program that looks into the compiler's known definition of your type, see what's missing, write functions that basically will be your wrapper, and inject that wrapper into your program. So I think we are covering your case.
We are going with the last two questions.
Hi, I was really curious to hear your opinion on what you think the next 40 years of C++ are potentially like. So over the last 40, there's been a lot of new standards and features every few years. Just wondering if there's any plan to deprecate old features, or if you think we're just going to keep adding new things.
A good question and a hard question. I'm not good at thinking about 40 years. 40 years ago, I had some ideas, and some of them were facilities I wanted in the language, and some of them was about what I would do about ideas I might get in 10 years. The idea that the language evolves. And the idea about how to evolve hasn't changed. I think we will find things, and we have to work on how to get things in. I have become more convinced that you can't break old things. With billions of lines of code, you don't actually know who you would hurt when you take a feature out. We have tried several times, they've always failed. The general idea of taking things out is to deprecate them, tell people in 6 years they're gone. Please update your code. It doesn't work. People don't do it. It's as simple as that. and then the implementers come back and says, I could do what we thought 6 years ago, but I'm told by my major users that they will go and clone the compiler or go to the competition. We will not. I cannot afford to do that. This has happened repeatedly. There's been suggestions that you do automatic updates. That means that you have to have a full understanding of what it is you're updating, which is unlikely. And anyway, the technology for analyzing and doing code transformations in C++ is not as good as I would like it to be. I'm pushing for that. Okay, so what would I like to see? That is, we're now talking 5-10 years, not 40. I would like to see functional programming style pattern matching in place, Lisp comprehension or whatever you want to call it. And we have, unfortunately, 2 designs for it, and that stalls in the standard, because standards process. But basically, if I can get that, I could write some code more concisely, more precise, and with fewer opportunities to make mistakes. And we have pretty good designs. If you go to a website called WG21, you can find all the papers and all the proposals, and I'm in favor of the functional programming ones. Functional programming pattern matching ones. What a name. Anyway, the other one I'm interested in and pushing is static reflection, and static reflection I'm very hopeful for in the near future. There's also work on a general model of concurrency, more general than what we've got, based on senders and receivers. This is in production use at Meta and NVIDIA, so most of you will have used it today. This may also again get into the standard for 26, but it was scheduled to get into the standard in 20, and the problem is people keep getting great new ideas, and so it doesn't come in because we just need another couple of years. So evolution is hard, both because you can't get rid of old things and because people start getting new ideas and the constraints change during the design process and such. It's not easy. I want more support for ranges. I mentioned that kind of programming, more type deduction, and then we go to the tools. C++ is deficient in the tool support. Quite often the problem is not that it doesn't exist, but that the problem is that we have 5 different versions of, say, build systems. Well, CMake is winning, but it didn't always, and we still have many build 2 and such. And then package management we could really do with something like that. Traditionally, the ISO has banned us from working on that. We are a languages group, and tools cannot be standardized under a language. We are currently basically ignoring that, but we'll see what happens. And if nothing else, the fact that we work on it, even if it cannot be standardized under the ISO rules by our committee, doesn't mean that the implementers can't agree on something. One of the nice things about a standards committee is that we are not a cartel. If the builders of build systems or package managers got together and decided what the world should look like, it would be a federal offense. It's a cartel. If they do it as part of a standards committee, it's a public service. This is one reason I work with standards, even though it's quite frustrating at times. And if you want something done, there's the Spanish representative.
We have one more question, and then I think we'll be done.
You mentioned that the transition from include to import is hard. Do you have any tips or recommendations about that process, that transition? And do you think there's any hope that this process, this transition, can be tool assisted?
Not quite sure I understood.
From the transition from including headers.
What?
Moving from headers to modules.
Oh yeah, thanks. Okay. I think people just have to, as it were, bite the bullet, and library vendors should ship two versions, the module version and the header version. And for a lot of libraries and a lot of code, you can just build the header version and then have a module that says include the header and then export parts from it. It's a bit of work because you don't want to re-export everything you imported. The include file will contain a lot of junk you do not want to re-import. But I think that eventually has to be done. And the benefits are major. And for that reason, I think it's worth people's while. There's no way the standards committee can force people. And furthermore, you can't even force the compiler vendors to do a good job of, say, module implementation. So it's hard. We're fighting 50 years of history and billions of lines of code and many tools and compiler vendors. So it's going to be difficult, but it's happening. I'm doing most of my work in modules now, but I'm not building million-line codes with importing things or including things from a dozen independent organizations. But I think going to provide a module version in addition to what you have before, and then waiting and seeing what your users are doing, encouraging them to get the benefit of the modules might very well done. I was just hearing Qt is going that way, for instance. That's an important thing. It's a huge library and systems thing, so it's hard, but the benefits are there.
Okay, thank you very much, Bjarne. Thank you very much for coming to University Carlos III again, which is your home, and you are always welcome. And thank you, everybody, for attending.